We'd like to take a moment to recognize the generous support of the NEECECON sponsors, Advanced Energy, Techmark, Keysight Technologies, Embedded Silicon Technology Solutions Corporation, Meralco, Analog Devices Incorporated, Presidium.ph Corporation, Road and Schwarz Philippines Incorporated, Alexan Commercial Maker Lab, Samsung Electronics, Philippines Corporation, and Challenge Systems Incorporated. Good afternoon. We'll be starting our technical session 6 with a theme of national development through sustainable industrialization with artificial intelligence and smart cities 3. Our first presenter is about an indoor smart farm sensor node with energy harvesting system by Mr. Brian Bascos. Mr. Brian Bascos is a sensor development assistant from CARE Electrical and Electronics Engineering Institute, UP Diliman. Please welcome Mr. Brian Bascos.
So good afternoon, everyone. Welcome to NEECECON/ASTICON 2024. My name is Brian Christopher Bascos, and I will be presenting our project with the title, An Indoor Smart Farm Sensor Node with Energy Harvesting System. Let's start with the background of the study. So in smart farm applications, wireless sensor nodes are used to monitor environmental parameters such as temperature, humidity, ambient light, but also soil quality parameters, water quality, and air to ensure ideal growing conditions for the plants. So why energy harvesting? So one problem with wireless sensor nodes is that they typically run on batteries for portability, but this may also introduce a challenge. Manually replacing batteries can be time-consuming and limits deployment locations. So the solution is to extract energy from the environment. Since there are various ambient energy sources and they're not being used, it can become more sustainable and could theoretically power the wireless sensor node for an indefinite period of time. So it's not a very new idea already, but we have these example previous works, such as Sadowski and Spachos reported a longer wireless sensor node lifetime when a solar energy harvester was equipped. Sharma and Jaffery observed better network performance with energy harvesting. And finally, Kelby et al. Demonstrated that it is possible to harvest enough energy from indoor office lighting. So we're not limited to harvesting solar energy outdoors. So this is a quick comparison with similar works. So our project will be using LED grow lights as light source with BQ25570 as RPM IC, a supercapacitor for energy storage, and the network protocol of sub-gigahertz. For the system overview, the energy harvesting module has 3 main components. First is the photovoltaic cell, which harvests energy from LED grow lights. The power management unit, which regulates the charging and discharging of the storage element. And finally, the energy storage, which stores excess energy for use when grow lights are not available. The system load will be the sensor node based on LPSCK CC1352R. Let's move on to the software. So as I've mentioned, this wireless sensor node for our project, we use the sensor tag kit from Texas Instruments. The CC1352R has HDC 2080, which is a temperature and humidity sensor, and an OPT3001, which is an ambient light sensor. We transmitted the data over sub-gigahertz protocol. So on the right side, we can see a basic flow chart of the operation. First, we open the I2C and RF modules, and then we read sensor data and transmit it. And then we close the I2C and RF modules so that they're not consuming energy at the background. And then the system goes to deep sleep for 5 minutes. But the problem is that in indoor smart farms, the grow lights used as an alternative to the sun, they have to be turned off periodically. So there are times when we cannot harvest energy from them. So the solution is to adjust the sleep duration according to the remaining charge in the energy storage device. So the green blocks in the updated flowchart are the energy-aware operation that we implemented. So when the loop starts, before we go on to the sensor processes, we first measure the battery voltage from ADC and then adjust the sleep duration, T-sleep, using adaptive transmission algorithm. And then we also implemented a sort of trigger in which whenever the light state changes from off to on or vice versa, it will execute an interrupt with the light sensor, which causes the sensor node to wake up prematurely and send data. So this is the energy-aware decision table. So as we can see, when the lights are on, we only have 2 states, and the sleep duration ranges from 1 minute to 5 minutes. But if the lights are off, we have 4 different states, and the sleep duration ranges from 5 minutes to 60 minutes. So this is the current drawn by the active state of the wireless sensor node. This figure is taken using TI Code Composer's energy trace feature. So remember that in the active state, it has 1 spike, 3 small blocks, and a big block. Because this is the breakdown. The spike is the initialization process. The 3 small blocks is the sensor processes, and the big block is the transmission. And the deep sleep consumes around 8 microamps of current, and the total active period lasts for 20.5 milliseconds. And the active period consumes about 3.14 millijoules of energy. Moving on to the energy harvesting module. For the energy storage, we had 2 options. The first is the rechargeable batteries, but they typically have lower charging cycles, so an application where they are recharged often may cause quicker degradation. So instead, we used supercapacitors, which can support more charging cycles, but the drawbacks are that its voltage output decreases as it discharges, and it also has smaller capacity. Speaking of capacity, this is the table form of the graph I showed earlier. So we can see that the total of 1 cycle consumes about 2.415 millicoulombs. But in 4 hours, it consumes 116 millicoulombs. Based on the current profile of the wireless sensor node and assuming a leakage current of 10 microamps, the supercapacitor must have at least 130 mF capacitance. For the photovoltaic cell, we had 3 choices. First is the AN276 monocrystalline, the MP337, and the SM141 K06LV. So this is the efficiency test that we did, and according to the results, the SM141 displays the highest efficiency for any given lux level. So the SM141 is the one with the yellow bars, so it's quite far ahead among the other 2 choices. And the SM141 also has the highest power density among the choices. So it became our primary choice for PV cell. Then for the power management unit, we used a solar energy clickboard from Microelectronica. It's based on BQ25570IC, which has a boost charger to match the input voltage to the required charging voltage, and a buck converter to stabilize the output voltage going to the load. It also has a built-in 220 mF supercapacitor, which is more than enough since the minimum capacitance that we need is 130. But there are also options to add another storage element. So we performed a charging test. So first, we used a single SM141, the red graph, and it took 33 minutes and 42 seconds. So this is the charging time of the 220 mF supercapacitor under 3,000 lux. As we can see, it was a little too long because apparently, even though the SM141 has the highest efficiency and power density, its actual power output was not enough. So we decided to connect 2 SM141s in parallel, and it reduced the charging time to 8 minutes and 47 seconds. That is the green graph, green line. We also had a 3D printed enclosure to protect the components. Let's move on to the discharging experiment. So our experimental setup, we used an oscilloscope to monitor the Vout, which is the output voltage of the PMU, and Vbat, which is the voltage level of the supercapacitor. And a collector node based on the Launchpad XL CC1352R1 receives data from the sensor node. So you might be wondering why there is a voltage divider going into the sensor node to measure the Vbat. It's, di wala nalagay. Sorry. It's because the GPIO pin for ADC was constantly drawing 8 microamps of current regardless if the sensor node is on or off. And due to time constraints, we weren't able to solve the issue properly. So we had to use a voltage divider to minimize the effect to about 3 microamps. So going back to the results, this is without energy aware, and the supercapacitor operates between 4.2 volts to 2.6 volts. With the 1 minute sleep duration, the wireless sensor node lasted for 3 hours and 40 minutes when lights are off. But with an adaptive sleep time, the wireless sensor node lasted for 5 hours and 10 minutes, which is much longer. So this is a side-by-side comparison with proper proportions. So finally, to wrap up our project, so we used an LPSTK CC1352R as a low-power autonomous wireless sensor node. We implemented an energy harvesting module composed of an SM141 K06 LV PV cell, a PMU based on BQ25570, and 220 mF supercapacitor. The batteryless operation was sustained for more than 5 hours of darkness, and the adaptive transmission rate increased lifespan of the wireless sensor node by 40% compared to a constant 1 minute transmission rate. As for our first recommendation, it would be to use a custom PCB for the BQ25570 instead of using a commercially available one, because not only this will allow the researchers to maximize the supercapacitor's operating range, it may also be possible to address the GPIO drain issue that way. Longer sleep duration may be explored, in which case less frequent transmissions, since plant doesn't really grow that much in minutes. Another recommendation would be to use energy storage with bigger capacity. And finally, the replacement cycle, one thing to consider is to consider the replacement cycle of sensors with regards to the crop cycle. And this is our works cited. Thank you.
Okay, thank you for that presentation. We actually have time for questions. Anyone? Okay, I'll ask a question. So, what were the key challenges in implementing this algorithm? And relative to the literature, what makes your method more efficient, aside from using supercapacitors?
In terms of the implementing the software, we did not really have much of a challenge, except that there was a learning curve because Texas Instruments have their own proprietary IDE, which is a little bit hard to learn at first, but yeah, the software was not much challenging. But in terms of the hardware, the main challenge was the delivery time of the components that we needed. That's why we weren't able to create a custom PCB for our project, and instead we resorted to using a commercially available one.
Thank you, Mr. Vasco. So now I'll be presenting your certificate of appreciation for sharing their invaluable insight on work on an indoor smart farm sensor node with energy harvesting system during the NEECECON 2024, given this 19th day of July 2024 at Novotel Manila Araneta City, Quezon City, Philippines. Signed, Dr. Liu Andrew Tria. We can now proceed to our next presentation. AIoT-aided farm management for the optimized production of selected high-value crop. This will be presented by Mr. Melvin Ilang-Ilang, an assistant professor from the Department of Electrical Engineering, UP Los Baños. Please welcome Mr. Melvin Ilang-Ilang.
Okay, good afternoon everyone. I'm Melvin Ilang-Ilang. I'm from UP Los Baños, and I will be presenting our project entitled AIoT-Aided Farm Management for the Optimized Production of Selected High-Value Crop. Okay, and listed below are our team members. Quick background about the project. So the project was brought about by the MECO-TECO Joint Research Program and the National Tsinghua University in Taiwan. So actually, NTHU were able to work on this project first, but they focused on the production of dragon fruit. So just a quick background, dragon fruit is, the cropping cycle of dragon fruit is limited only to once a year. But NTHU was able to produce or to make it into 2 cropping cycles per year in Taiwan. Okay. So AIoT, so basically it's a marriage of artificial intelligence and Internet of Things. And so we are all familiar with artificial intelligence already, and then Internet of Things, like the previous presented project, it's also considered as an example of Internet of Things, the wireless sensor networks. So the outline of my presentation, first, I'll be presenting the needs assessment for this project. Next would be the theoretical framework, system architecture, field experiments, and the evaluation. So prior to the implementation of the project, we conducted a needs assessment, and we found out that in the case of tomato production, losses due to farm management inefficiencies were one of the major problems observed in a prior needs assessment and technology intervention studies conducted. Okay? So why did we settle in the tomato production? It is because of the proximity of UP Los Baños to the tomato farms available nearby, especially in the towns of Liliu, Santa Cruz, and actually even in Batangas and Cavite. And also, since our funding agency is DOST Picard, they advised us to choose a high-value crop. So tomato actually is considered as a high-value crop. So for our theoretical framework, we started with initial field verification. So we conducted focus group discussions with different farm associations and farmers in the, actually in the whole region 4A. Next, we conducted we determined the design considerations, conducted laboratory testing, field deployment, data gathering, modification and calibration, and lastly, the evaluation. So for the system architecture, it can be outlined using this block diagram. So we have actually 4 main components for the whole system. We have sensor nodes. So the sensor nodes, or as we call it in our project, the sensor poles, are strategically placed on plots so that we can measure the different environmental parameters vital for the cultivation of tomato. And then these sensor nodes are connected wirelessly to a master node, which then instructs the actuator node on what to do with respect to fertigation. And then the master node also sends the measured parameters to an online dashboard, which can be accessed remotely using any device. For the sensor node, here are the key parameters that we measured. So these 4 parameters were based on the parameters vital for the growth of tomato. So we employed temperature sensor, relative humidity sensor, soil moisture sensor, and we built in an LDR module to measure the PPFD and light intensity that goes into the crop. Okay? And then the microcontroller unit that we used has an embedded LoRa module to balik lang natin yan, to communicate with the master node. So why did we choose LoRa module? From prior needs assessment, based on the terrain of the farms that we have visited, the most appropriate wireless communication protocol to use is the LoRa or long-range module. Okay, for the actuator node, for this study, we focused on the water requirements depending on the growth cycle of the plant. So besides the water requirement, we also integrated the fertilization or the application of fertilizer in the crop. So again, the microcontroller used here has an embedded LoRa module so that it can communicate wirelessly with the master node. So for the master node, again, it has an embedded LoRa module. Besides that, we added also a Wi-Fi module so that it can upload data in real time to the online dashboard. Besides the data being sent to the online dashboard, we also added an SD card module so that the master node can save data locally. So if ever that we can't send the data to the dashboard, the data can still be recovered via the SD card connected to the microcontroller unit. So here is a snapshot of the dashboard that we used. So actually, we utilized ThinkSpeak API so that after getting all the data required, we can immediately export the data to MATLAB. Just a quick background, this project is a phase 1 of a program that we are developing. So we are still in the process of the continuation of the project. Yeah, so here we can see the time series graph of the parameters measured based on the readings from the sensor nodes. And for the field experiments, this is the example of one of our implementations. We planted or we utilized 6 plots for this experiment, and then per plot there is a different treatment. So for example, for block 1, plot 1, the treatment used was automated fertilizer application and scheduled irrigation. And then for block 2, plot 1, automated fertilizer application, then reactive irrigation. So the plots here actually has different treatment for irrigation. So first is the manual irrigation, next is the reactive irrigation, and then scheduled irrigation. So what are the differences of the three? So for the manual irrigation, this served as our control setup. So the manual irrigation is based on the farmer's practice on when they apply water to the plants. And then for reactive irrigation, so the actuators deliver water based on the measured relative humidity and soil moisture sent by the sensor nodes. And for scheduled irrigation, we just added this one because the farmer that collaborated with us in this implementation said that for their farm, they don't actually use the manual irrigation method. Instead, they have a scheduled one. So they water the plants in the morning and the afternoon. So we also implemented that one. And then for the fertilizer application, so for the manual fertilizer application, this is the base from the farmer's practice again. And for the automated fertilizer application, this one is scheduled based on the plant requirements, depending on the growth stage of the tomato. And this is the actual test site. So the one on the left is the master node. So there is a graphical user interface wherein the farmer can view the real-time updates from the sensor nodes. And also, he can, or the farmer can turn on or off the irrigation and fertilizer application. So the irrigation method that we used here is drip irrigation to have better control of the volume of water. And then, as you can see, I hope you can see the sensor poles. We have two sets of sensors here. One is located about 1 meter from the ground, and the one is located about 0.2 meters from the ground. So the reason for having two sets of sensors here is that so that we can address the different growth stages. Okay. So the one on 0.2 meters from the ground measures the parameters while the plant is still a seedling. And then the 1 meter, the sensors located 1 meter above the ground addresses the issue when the crop is already at the fruiting stage. So for the evaluation, we performed hydraulic performance evaluation based on these three parameters. So coefficient of variation, coefficient of uniformity, and emission uniformity. So based on our results, we determined that for CV, we have an interpretation of excellent. And then for CU, we have very good performance. And for EU, we have good performance. So this is based on the implementation using drip irrigation. Also, we measured the yield from this setup, and then we found out that the scheduled irrigation setup has the highest yield. Okay, so for scheduled irrigation and manual fertilizer application, it has 8,950 kilograms, and then for scheduled irrigation and automated fertilizer application, it yielded 8,525 kilograms or grams. I might correct that one. We also performed statistical analysis. So it was found out that for scheduled and reactive irrigation, there is no significant difference between the yields of the two. And their yield is significantly different for the manual irrigation treatment. And then we also performed cost-benefit analysis. So based on these numbers, we determined that for, depending on the farm gate price, so we categorize it to low, medium, and high farm gate prices. So if the farm gate price is low, the return on investment would be 2.51 years. Okay? If you consider one cropping cycle per year. For medium farm gate price, the return on investment would be 1.79 years. And for high farm gate price, the return on investment would be 1.33 years. And then we measured, based on our experimentations, the usable life for the device that we have created is for 5 years. So if we can utilize the device for 5 years, we can expect that the investment made would be put into good use. So for future enhancements, we can incorporate machine learning for optimized decision making and utilize data for informed farm management practices. That's all. Thank you.
Thank you, Mr. Melvin. We still have time for some questions from the audience. Anyone? Okay. I do have a question for Sir Melvin. I'm not sure if I missed it, but how many plants were used during the testing, and how significant is the size of the test size to determine the accuracy of the results?
Yeah. For the one presented here, we planted 4 plants per treatment. And actually, this was already computed by a statistician. This was recommended to us.
Thank you. Any more questions from the audience? None. Okay. Last question from me. Despite the efficiency of your method, what are the barriers that our farmers face to be able to adopt this technology?
Based from our FGDs conducted, their main concern is pilferage actually. When they learned the cost of this system, they fear that when they deploy it in their farms, that baka lang nakawin. So yun yung isang malaking concern nila. And of course, since yung mga nakausap namin ay hindi naman sila yung corporations talaga, so yung initial cost doon sa pag-adapt ng technology, yun yung isang malaking concern nila.
Okay. Thank you, Sir Melvin. Now we can proceed with the awarding of certificate. Okay. Certificate of Appreciation is presented to Sir Melvin Ilang-Ilang for sharing their invaluable insight and work on AIoT-aided farm management for the optimized production of selected high-value crop during the NEECECON 2024, given this 19th day of July 2024 at Novotel Manila Araneta City, Quezon City, Philippines. Signed by Dr. Liu Anru Tria. For our third presenter, we have leveraging Earth observation and social media data for timely disaster impact assessment in the Philippines that will be presented by Ms. Nikki Cadiz. Ms. Nikki Cadiz is a senior science research specialist from DOST-ASTI. Please welcome Ms. Nikki Cadiz.
Hello po, good afternoon. So, I'm usual Ronic Arcadis, katulad ng sabi ni Dr. Jean kanina, Dr. Merrill. So you can call me Nikki for the sake of this presentation. So I will be talking about the social media data that we have been using for timely disaster impact assessment in the country. So I'm really sorry, hindi ako mapakali na nandito lang ako, so I need to come here. Kita naman, no, kasi maliit naman akong tao. So for the clicker, let's go. For my first presentation, if you can see this, do you know that we have the World Risk Index? So yung World Risk Index natin, dito natin makikita kung gaano ka-risky ang isang country sa disasters or sa hazard. So I'm a bit, I don't know, kanina iniisip ko kung ilalagay ko pa ba to kasi it's an outdated slide na. This one is still from 2022 and I have presented this paper or this presentation in 2023. So the data that I have now is 2022 lang. So in 2013, do you know what happened in 2013? Yes, naka-smile lang sila sa akin. But in 2013, Super Typhoon Yolanda. In 2020, I don't know what happened here, pero in 2013, nasa number 3 tayo for the World Risk Index. In 2020, number 9 na tayo, medyo bumaba na, di ba? Pero as palaging mga nananalo sa mga pageantries natin, Miss Universe, number 1 na naman ang Pilipinas noong 2022. Bakit? Sorry. Parang may nakita akong pumalakpak. Number 1 na ang Pilipinas. Huwag niyong palakpakan na number 1 ang Pilipinas kasi hindi to okay. So yung Pilipinas noong 2022 is number 1 in the World Risk Index. Meaning, mas mataas na tayo compared to Vanuatu as well as Tonga, which are the countries na literally every month, every day, meron silang hazards, disasters, and everything because located sila sa, or literally napapaligiran sila ng tubig. So inevitably, Vanuatu and Tonga are the countries that have the highest risk in terms of disaster. So, in 2022, nakakabahala lang. So, isa na naman to. Pero, what I would just want to tell you is that, number one, ang Philippines, kaya lang, this is because of many other factors as well, like economy, societal impact, and everything. So, there are a lot of factors naman on that one. And I also want to remind everyone that the Department of Science and Technology is part or is heading the Disaster Prevention and Mitigation Program ng gobyerno natin. So we have 4 thematic areas and the DOST is the lead for the Disaster Prevention and Mitigation. That's why we have projects and services like ours na ipapakita ko sa inyo later kung anong ginagawa namin. And I think Doc Merrill mentioned this kanina, pero I think I am the only speaker for this session na from DOST-ASTI. So I will give you information, a little bit information about DOST-ASTI. DOST-ASTI is the lead of the ASTICON right now, yung collocated event po natin. But aside from that, DOST-ASTI is one of the 9 research and development institutes of the Department of Science and Technology. So, maraming RDIs ang DOST, but the DOST-ASTI is focusing more on microelectronics, electronics, ICT. We also delve into space science and technology mga bandang 2013-2017. And speaking of space technology, ito yung focus ng talk ko ngayon. So ito yung mga space science and technology assets that DOST had funded. Kasi these assets are now transitioned to the Philippine Space Agency. So meron tayong dating Pedro Center. Si Pedro Center, in essence, sila yung nakikipag-communicate sa mga satellites natin. So marami tayong mga satellites, marami tayong subscription, marami tayong pagmamayari, Diwata 1, maraming mga satellites assets sa buong mundo. And si Pedro Center, sa mga meron tayong subscriptions, sila yung communicate. So essentially, what they do is that they upload commands to those satellites, and whatever those satellites did, especially in taking satellite photos, satellite images, dina-download ng Pedro Center. Then, there was DATOS project and there is Sarwise project. So si DATOS project and Sarwise project, kami yung nagpa-process ng mga satellite images na yon to something, translated into something na maiintindihan ng mga local government unit officials natin or yung mga students. Magpapakita po ako ng examples later. And we also had the Stamina for Space. This one naman is a project under the University of the Philippines and in cooperation or in partnership with DOST. So ang topic ko ay about sa pag-leverage namin ng social media data as well as any other information, education, and communication campaign using these space science and technology assets. So one of the DRRM efforts and initiatives ay yung pag-produce namin ng mga automated flood impact maps. So later, makikita ninyo yung mga maps na na-generate namin. Pero si DATOS as well as Sarwise, nagdi-distribute kami ng mga flood impact maps and other datasets to national agencies. So national agencies include DOST regional offices, pero meron din kaming mga partners like the Office of the Civil Defense, Pag-asa, National DRRM Council, so lahat ng mga DRRM agencies sa buong Pilipinas. So itong mga maps na ito, binibigay namin via social media, via email, And recently, meron na rin tayong Viber group para mas mabilis or para mas seamless yung information flow. And what is needed or what we saw na very effective dito sa disaster management effort namin was to actually request data from people online. So what we did, nagkaroon kami ng participatory data request. So we asked our followers sa social media as well as yung mga ibang tao sa Instagram, Facebook, Twitter to give us information on what is actually happening on the ground. So sila yung nagbibigay sa amin ng satellite image, no, not satellite images. Sila yung nagbibigay sa amin ng mga photos. Kunwari flooded sa lugar nila or kunwari nagkaroon ng landslide or merong earthquake, sila yung nagbibigay ng photos sa amin. And given those photos and the information coming from those people, pinaplat namin yung information na yon sa mapa. If you can see, dito sa side, pwede pa po ba to? Dito sa, I don't know, sa left side, ito yung mga photos na nakita namin sa Facebook and Twitter, as well as mga links or yung mga pangalan ng mga tao na nagbigay sa amin yan. So since meron na tayo, natanong na natin, kunwari sa Ilocos Norte, meron pong flooding, this is the flooding, ito yung photos, tinatag namin, saan sa Ilocos Norte? Kung sasabihin niya sa Lawag, okay, let's tag Lawag as the area na actually merong flooding. So nagkakaroon tayo ng geography, ng coordinates na pwede natin gamitin to tag sa mapa natin. And since meron na tayong mapa, alam na natin kung saan yung concentration ng hazard, kung saan may flooding, saan may earthquake. Ang ginagawa natin ay mag-produce na tayo ng maps. So yun na po yung nangyayari. Si DOST-ASTI project, kino-complement na namin yung disaster management system or yung mga efforts ng mga DRRM agencies natin. So ito na yung mga mapa na na-produce natin. So with that, ayaw niyang mag-next. Sorry, ayaw na po niyang mag-next. So ayan, ito yung mga examples ng mga nagawa natin mapa. Meron, kung naalala nyo po, or nagawa nating mapa or mga nagawa na nating mga initiatives, kung naalala nyo nung 2022, nung nagkaroon ng earthquake sa Northern Luzon, Abra, so nagbigay tayo agad ng data sets sa mga taga-Abra, taga-Ilocos Sur. Meron ding ditong data, participatory request din to, nakita natin kung saan yung concentration nung disaster. And ganyan lang po siya, ito yung mga data sets natin. Nagkaroon tayo ng mga areas of interest for satellite tasking. So kapag napin na natin sa mapa, itatask na natin yung mga satellites natin kung saan magtitake ng photos. Kung nakapag-take na sila ng photos, magda-download tayo ng mga satellite images and then ipaprocess natin. So ganyan po siya. Northern Luzon earthquake, meron din kami sa Metro Cebu, and any others. So ang motivation lang why yung mga technologies natin ay naka-angkla sa mga disaster. Number one, na meron talaga tayong mga data sets is for the flooding in the Philippines. Kasi recurring dilemma siya in the Philippines. So nagmamap tayo ng mga flood extents. So meron tayong service on that sa DOST. Gamit ang Novasar satellite and other satellites na free that we could use. So si Novasar satellite, just a quick background, merong 10% imaging capacity ang Pilipinas. So if ever na kailangan ninyo ng satellite images from the Novasar satellite, meron tayo kasi nakakakuha tayo ng 10% na share from the Novasar tasking. So yung 10% na yon ay everyday siya, 2 beses nagtitake sa Pilipinas. It amounts to 180 seconds of imaging time. Is it every day? Every day. Basta 180,000 imaging time siya. Or I don't know, for the whole na po pala siya. So yung acquisition ay through the Sarwise project, and the download and communication is still with the Pedro project. So nakita dito, the images can help address the potential gaps in data availability kung walang available na data from our other satellite assets. Ito lang po yung general workflow namin, methodology lang siya. I was supposed to actually present this yesterday sa isang session din. Pero for some reason, hindi na-present, so dito na lang po siya. Ito yung general workflow namin. Image tasking, map generation, and then map distribution. As is lang siya, pero maraming nangyayari on the ground. So if you can see that, ganyan yung flow na na-develop ng project team namin. So nagpe-pre-process din kami ng mga Novasar images using this. So if you want to ask questions later about this, I cannot answer that because our technical people are actually the ones who develop this. Pero if just in case hindi nyo maitutulog ba maya yung tanong ninyo, meron namang someone here na pwedeng sumagot ng tanong ninyo mamaya. So, mayroon tayong flood extents generation din. So, ganito rin yung process namin. If you want to ask that later, later na lang po. And ito na yung mga generated maps natin. Aside from flooding, marami pa tayong ibang mga maps na pwedeng magawa. So, pwede tayong mag-assess. Kanina, I told you about this, pwede tayong mag-assess ng flood damages from those satellite images or from those processed satellite images. We can also monitor the volcanic activity of our volcanoes sa Pilipinas. So this one lang, just a technology demonstration, meron tayo or kaya natin gumawa or gumamit ng interferogram for that. So, kausap po namin ang DOST-FIVOX dito. So, si DOST-FIVOX, sila na po yung gumagawa neto, but it came from DOST-ASTI, yung mga tools na ginagamit nila. Flood extent po ulit to, but this one is specifically for Novasar. And kaya natin magbigay ng mga satellite images for post-typhoon disaster assessment. So if you want satellite images for your local government units or for your communities, pwede po nating ibigay ito. And yeah, disaster assessment, disaster response, earthquake damages, forest fire, kaya po natin mag-assess niyan. Meron din po tayong object identification using those satellite images. Sorry, I only have a minute left, but in 2021, for us to actually disseminate or meron tayong technology transfer na ginawa. In 2021, na-task kami ng DOST to disseminate or to ipakilala tong technology na to sa mga government officials natin, government units, as well as state universities. So, nagkaroon tayo ng mga regular training series from Luzon, Visayas, and Mindanao. May mga training request tayo. May mga outputs yung mga estudyante natin. I don't know if nandito pa rin po sila. Ito yung mga na-train namin. And then, program of instruction. Ito yung nagamit naming tool. Na-train natin ang PSA, na-train natin ang SRA, na-train natin ang LLDA. So, Department of Transportation, FIVOX ACER. And if you want to ask question, if pwede pa po bang mag-training, sorry, hindi na po kasi tapos na po yung project namin nung June 2024. So, the challenges and everything, marami kaming collaboration, data distribution, licensing. Itong mga to makikita nyo lang sa mga sites ng mga partner agencies namin like FIVOX. And ito yung, just to end the presentation, ito yung mga technologies na pwedeng magamit or pwedeng maging output for satellite images or Earth observation satellites. So I won't have time for the conclusion, but thank you very much po. If you have any questions, ito po yung mga contact details namin. Thank you.
Thank you, Ms. Nikki. So we have time for, I think, one question. Oh, wow.
No.
Hello. Hi, good afternoon, Ms. Nikki. So, I'm Leo pala from UP EEEI. So, regarding your, your efforts on the crowdsourcing during the flooding and other disasters, do you have like a system in place to verify the inputs of the general public, whether for the photos that they are uploading, whether yun talaga yung condition on the ground, or if it's just perhaps an old photo from somewhere else, or kaya na-download lang nila from Google that they send to you. Ayun lang. So, method for verifying the crowdsourcing inputs. Thank you.
Thank you, sir. So, hindi ko maalala na may mental block ako kung anong tool yung ginamit namin for this. Pero for the method of verification, number one na ginagawa na namin ay dina-download namin yung images and extract the metadata. If those images are not taken on the day na binigay nila yung photo or on the place that they actually told us na doon nila tinake yung photo, hindi po namin yung kinukuha. So, kapag na-collate na po namin lahat ng mga images na actually verified na binigay ng mga tao from the internet or even yung mga partners natin on the ground kasi maraming naman po tayong regional partners. Kapag na-verify na po yun, ang ginagawa natin, tinatawagan na po natin si DOST Region 1 kunwari. Totoo po bang umuulan? Totoo, yung earthquakes, mabilis naman pong malaman kasi may FIVOX. Pero tinatanong natin, totoo po bang may flooding? Totoo po ba na may na landslide dito? And then, those DOST regional officers will tell us na opo, totoo naman po siya. So kapag sinabi po nila, ang ginagawa na natin ay pinaplat na po talaga natin sa mapa. And even before, nagpa-process na tayo and then we give those maps as well as raw data na po to the local government unit officials through the DOST region office or the DOST, yung PTSO, yung sa provincial office na po nila. So, yun pa.
Thank you,
sir.
and congratulations.
Thank you, sir. So, ayun po. Do you have any other questions? I think one lang, Doc Meryl, no? So, thank you po.
Okay. Now, I would like to present the Certificate of Appreciation to Naciel Ronique Cadiz for sharing their invaluable insight and work on leveraging Earth observation and social media data for timely disaster impact assessment in the Philippines during the NEECECON 2024, given this 19th day of July 2024 at Novotel Manila Araneta City, Quezon City, Philippines. Signed, Dr. Lou Andrew Tria. We can now proceed to the next presentation of enhancing the robustness of speech foundation models through adaptation on large-scale diverse speech that will be presented by Ms. Jessan Rendel Belenzo, Masters of Engineering AI student from Artificial Intelligence Program, UP Diliman. Sorry, Mr. Jessan Rendel Belenzo.
Hi, good afternoon. So my name is Jessan, and I am a Master of Engineering and AI student from UP Diliman, and I'm presenting SpeechX, enhancing the robustness of speech foundation models through adaptation on large-scale diverse speech. So to understand SpeechX, we must first understand large language models. So tokenization is a important pre-processing step for training large language models. So for example, here the sentence, "It is raining." This sentence can be partitioned into characters, as shown in the first row, or by word, as shown here in the second row, or by subword, which is a compromise between character level and word level tokenizations. So it is important to note that the tokenization process is completely reversible. So it means that if you encode a string into token IDs, you can decode the token IDs back to its text representation. So ChatGPT and other commonly known LLMs write essays, answer questions, or make recipes just by trying to generate the next token in the input sequence. For example, if you input the cat to the LLM, it will for example, the output of the LLM is SAT, the word SAT is appended to the input prompt to generate the new prompt, the cat SAT. And this process is iteratively performed until it reaches the end of text token. And this approach is called autoregressive language modeling. So we now proceed to Speech GPT, which is the backbone model of SpeechX. So Speech GPT is a foundation model, which is cross-model. So it means that it can understand inputs and produce outputs in either text, speech, or both modalities. So here, it can perform text generation. It can perform speech-to-speech task, or text-to-speech. And lastly, automatic speech recognition. So how does Speech GPT, which is a LLM-based model, do this? So the key here is that the conversion of speech recordings to a representation that LLMs can understand. So the example here is for the ASR task. So the speech recording is passed onto the UBERT tokenizer to generate the discrete codes. And these discrete codes consist of integer tokens wrapped by start and end of speech tokens. So this discrete code is appended to the input instruction, and the concatenated sequence is passed to the cross-model instruction generator, and the final instruction is fed to the LLM to generate the transcription. So the training process of Speech GPT consists of 3 stages. So the first one is modality adaptation, which is also called pre-training. So the model is pre-trained on pure speech tokens. So the dataset used here is Librelite dataset. So for the second stage, it is cross-model instructions. So in cross-model instructions, the model was fine-tuned on ASR and text-to-speech instructions using LibreSpeech, GigaSpeech, Common Voice, and MOS002 SFT dataset. And lastly, for the third stage, chain of modality instructions, the model was fine-tuned to discourage illegal, obscene, or toxic responses using the MOS002 SFT dataset. And the main issue here is that Speech GPT was pre-trained exclusively on Librelite, which is a dataset consisting of narrated speech recordings. So the problem here is that it may not perform well on speech recordings on other speaking styles. So to address the problem, we further trained Speech GPT on a diverse collection of speech datasets based on the end-to-end speech benchmark, as shown here in the table. So these are the 4 datasets. So the first one is LibreSpeech. It consists of narrated audiobooks. The second one is Vox Populi, which consists of oratory speeches. Third one is GigaSpeech, which consists of audiobooks, podcasts, and YouTube videos. And lastly, SPGA Speech, which consists of recordings of financial meetings. So the total number of hours is 16,000 plus hours. And this is to cover a wide spectrum of speaking domains, acoustic environments, and speaker characteristics. So to develop SpeechX, we add GigaSpeech, Vox Populi, SPGA Speech, and LibreSpeech to the modality adaptation stage, and Vox Populi and SPGA Speech for the cross-modal instruction stage. Lastly, we do not fine-tune further the model for the chain of modality instructions. We evaluate SpeechX on the automatic speech recognition task using the word error rate. So word error rate, or WER, is computed using the sum of insertions, deletions, substitutions, all over the number of total words. So here in the example, the number of insertions is 1 since now was included to the ground truth. The number of deletions is 1 since the word the was omitted. And the number of substitutions is 1 since the word bark was replaced with bark, obtaining a word error rate of 0.5 or 50%. So we evaluate the model on each data set using the Hugging Face Evaluate library. So we noticed that for the LibreSpeech dataset, we obtained 76.7% improvement. For Vox Populi, it is 52.6%. For GigaSpeech, it is 59.3%. And for SPGI Speech, it is 80.8%. So I'm showing you a demo of the automatic speech recognition task that SpeechX can perform. So the ground truth here is the string, what are the main causes of climate change? So this is the demo for the ASR task. So the model will transcribe a speech recording.
What are the main causes of climate change?
So SpeechX correctly transcribed the speech recording input. So the next demo is text-to-speech. So here the model was prompted to generate speech from a transcription.
May the force be with you.
So it can also accurately perform text-to-speech tasks. And lastly, it can perform language tasks such as question answering. So to conclude, since SpeechX can perform a variety of speech-language tasks, we highlight its potential to advance the reliability and inclusivity of speech foundation models. However, one of the limitations is that it may not be representative of the performance of small language models, such as Phi-3 and Tiny Llama, since the fine-tuning was performed on a 7 billion parameter speech GPT model. And also, the focus of this project is on English datasets, which may limit the generalizability of findings to other languages, such as Filipino, Spanish, or French. So that's all. Thank you po.
Thank you, Sir Jessan. I think we have time for one question from the audience. Anyone? Yes.
So hello. If I'm not mistaken, your presentation is all about further fine-tuning speech GPT using other various data sets on some of its speech GPT's stages. How were you able to determine which data set goes to which stage? Were there any rules or that you considered, and like was it the size of the data set and so on and so forth?
So thank you for that question. So the rule that I used is that if the dataset in the original training is not included here in the proposed list of fine-tuning datasets, the datasets here will be included for the fine-tuning for the development of SpeechX. So for example, this so for example, in the second stage, Vox Populi and SPGA speech were not included in the original training stage. So we included it for the development of SpeechX. So that's all. Thank you.
Thank you, Sir Jason. So now let me present to you your Certificate of Appreciation. Certificate of Appreciation is presented to Sir Jason Rendel Belenzo for sharing their invaluable insight on work on enhancing the robustness of speech foundation models through adaptation on large-scale diverse speech during the NEECECON 2024, given this 19th day of July 2024 at Novotel Manila Araneta City, Quezon City, Philippines. Signed, Dr. Lou Andrew Tria. For our last presenter, we have Smart Instructional Laboratory or Smart iLab, a green, future-ready, and collaborative instructional laboratory for engineering education. This will be presented by Sir Ais Togonon. He is the researcher or engineer at Smart iLab project from Electrical and Electronics Engineering Institute of UP Diliman. Please welcome Sir Ail Togonon.
Good afternoon, everyone. I am Adrian Khalil East Togonon, and I'm here to present the Smart iLab project headed by Dr. JB De Guzman and donated by UPERDFI. For the outline of our presentation, we'll be first introducing the Smart iLab and its three main features, namely teleconferencing, IoT, and renewable energy. We first start with the teleconferencing setup of the Smart iLab and our mirrored lab setup. Next, we will talk about our IoT systems to create our IoT testbed platform. Then we'll briefly discuss our underlying infrastructure and finally the renewable solar energy system to power the classroom. So what is Smart iLab? Short for Smart Instructional Laboratory, it is a project that aims to redesign a laboratory in EEEI. The room will be IoT-driven with sensing and automation features and equipped with solar energy to power the whole room. We also designed a teleconference setup for hybrid learning where we aim to extend the scope of course delivery in EEEI. First, let's start with our designed teleconferencing setup. So the main goal of our teleconference setup is to extend laboratory courses outside Smart iLab. The recent pandemic has shown us the importance of remote or hybrid learning setups, but we want to enhance the functionality so we can extend course delivery to other rooms in EEEI if there's not enough space in the room. Another use case is to extend course delivery to other state university colleges that previously may not be able to host such a course. As Zoom is the most commonly used platform in the Institute, our system is mainly designed to facilitate remote learning and lab mirroring through Zoom. Other requirements that we identified is the ease of use, even for non-technical faculty or staff, which can be achieved with a plug-and-play system. With those requirements, here is our designed teleconferencing setup for the Smart iLab. The star of the show is an interactive flat panel with built-in whiteboard and content sharing features. We identified that 2 cameras, one for the lecturer and one for the audience, is needed to simulate an extended classroom feel. The cameras we use have auto-tracking features for an operator-free experience when lecturing. We also deployed a wireless conferencing hub called Barco ClickShare, where with just a USB-C dongle and a click of a button, you can share content to the screens from anywhere in the room. Both the interactive flat panel and the Barco act as a USB hub where you can access all of the peripherals with a single cable. For the mirrored setup, we have chosen the Department of Electrical Engineering in UP Los Baños as a pilot deployment. The setup we designed is very similar, with the only difference being a smaller interactive screen, no wireless conferencing hub, and a different PTZ camera. We will complement their current setup, where they have TVs, soundbars, and camera from the Picari Prime project, which will serve as our back TV setup. If you noticed from the 2 setups, we also want a front and a back screen, as well as 2 cameras for the lecturer and the audience always. This is so we can achieve our extended classroom vision, where the host can see who is in the mirrored classroom with the back screen, and the mirrored classroom will see the lecturer in the front screen. This goes both ways, such that either the Smart iLab or UPLB DEE can host each other. With this setup, we can extend or receive courses from other classrooms with a similar setup. Next, we move on to the IoT-driven features of the Smart iLab. This infographic shows all of the IoT services and features of the Smart iLab project. We'll talk about our IoT stack, which will be the backbone of our IoT testbed platform. We have a smart HVAC system to control the ventilation and AC, the smart lighting system for personalized lighting and wireless control, and we'll also talk about energy monitoring and at different monitoring levels, then our servers that provide the architecture to host these services. Finally, we will have our solar energy system, which will be powering the Smart iLab. The Smart iLab is supported by several locally hosted IoT services that allow the different systems to integrate and interoperate. Most devices that we use are Wi-Fi or Zigbee-based, so gateways are necessary to interface different communication protocols. We will be discussing these services and features that make them essential for the Smart iLab. Our main system integration platform of choice is Home Assistant, which is primarily used for home automation systems, but we extended its use case to a smart laboratory setting. It has the advantages of being locally hosted to avoid cloud fees and security risks, as well as system control even without internet. Being community-driven and open source, there's a wide range of integrations for many devices and interfaces. It also has a feature such as customizable UN dashboard, automation, scripts, and scenes. For the HVAC control, we opted to use the Sensible Air Pro Air Blaster to control our dome ACs. Sensible is cloud-based, but there is a HomeKit integration in Home Assistant for local control. It is better than regular Air Blasters, where you need to train all remote commands manually, whereas Sensible has built-in climate control already, as shown on the right. For the IoT stack, most of our sensors use the ESP Home system to configure ESP-based devices in Home Assistant. It's a simple programming language where you can write configuration files using ESP Home building blocks, which allows for easy-to-build and flash setup of many ESP-based home IoT devices. And here's the overall IoT stack that we are deploying in Smart iLab. We divided the room into 16 different zones for each workstation. Each zone will have their own IoT stack, which includes 2 Atom energy monitoring plugs, 1 Apollo air quality sensor, and 1 Apollo occupancy sensor. The lighting setup will also be divided into these zones for personalization per workstation, where the IoT stack can interact as well. The room also has air gradient 1 air quality sensor and 4 Apollo multi-target tracking sensors. And we also have Emporia View 2s for breaker level monitoring and sensible air pros, which we'll be discussing more in the future. For this occupancy detection, we used a millimeter wave sensors such as Apollo multi-sensor for each zone and Apollo multi-target sensors for general room occupancy. The MSR2 has 3 different configurable distance zones as well as per gate thresholds. And we chose this over MTR1 that has a relatively new LD2450 sensor, which has poor tracking against multiple targets and worse still detection. Shown here, we also have the specifications for the Apollo air quality sensor, which we deployed for each zone, and the air gradient 1 for general room monitoring. And as mentioned, we have smart plugs pre-flashed with ESP Home for workstation monitoring, and Emporia View 2 for breaker level monitoring. For Emporia, we can use the cloud integration to import aggregated data to Home Assistant. Once it is an ESP-based device, we can actually flash it with ESP Home configurations from the internet to get raw power, voltage, and current data. And this has actually been useful for us when we found that the base Emporia configuration only works for electrical systems with line-to-neutral configuration. And we had a problem that the building 1 of EEEI is in a delta configuration with no neutral. So we solved this by flashing a custom ESP Home configuration to derive the line-to-line voltage and get a correct power consumption. However, a limitation is that we cannot get the phase of the AC current from the current clamp. So there is a slight error due to an assumed power factor. Next will be the lighting system that we designed, which features a track-based setup to allow reconfiguration of plug-and-play lights due to the possibility of different room layouts depending on the usage for the semester. We have diffuse lighting for general room lighting and ambience, as well as focused lighting for personalized workstation lighting. Its brightness and color temperature can be adjusted, which allows for productivity research in the future. This lighting system is also Zigbee-based, which we will talk about more later. Here are some of the lighting renders of the 2 layouts where you have the front-facing classroom mode and the laboratory mode that is currently being used in Smart iLab. Our lighting system is based on the Zigbee communication that allows for wireless control and configuration of individual lighting fixtures. Zigbee boasts low power consumption and cost, has high capacity, fast response, and high safety. To integrate Zigbee devices with Home Assistant, we deployed a ZigStar coordinator as a gateway to the devices and a Zigbee to MQTT server to control the devices using the MQTT protocol. And as a background, MQTT is a lightweight publish-subscribe network messaging protocol that is usually used in IoT applications. With its standardized messaging format, it can provide platform-agnostic monitoring and control of IoT devices. It requires an MQTT broker, however, which we deployed an EMKX server in a Docker container, as shown here. One possible issue that can arise, though, is that the coordinator is a single point of failure for controlling devices using Home Assistant. To fix this, Z2M has the functionality of direct binding with the remote to still control the devices even when the servers are down. Another issue is Wi-Fi interference, since Zigbee is a 2.4 GHz channel as well, but this can be resolved with good planning of channel usage. So the long-term goal of the project is to develop an IoT testbed and platform for students to research in the future. The Zigbee lighting and ESP Home have MQTT integration that can provide platform-agnostic monitoring and control over these devices. A REST API server, or Node-RED, or Home Assistant can be developed to interact with the IoT platform. Research work on the IoT testbed is being performed by an undergraduate student currently called Sensor Fusion, where you can have air quality and energy consumption to predict occupancy using a Bayesian model. Another use case is an air quality mapping, where you can map air quality across different zones to see how pollutants move in real time. And while Home Assistant has its own database and graphing capabilities, we chose to have an external timescale DB database for storing time series data long term. We experienced data corruption due to power outages before, so we used StackRest to deploy a production-level database in a Kubernetes environment. It has built-in features such as replication, high availability, monitoring, and to prevent total data loss in the future. And StackRest also has a built-in Prometheus and Grafana server to monitor the cluster's health and database usage. Then, to visualize the data from the timescale DB, we use Grafana to show our data in a dashboard, where we can perform data correlation and validation, comparison studies, or just general live monitoring in a presentable format. And finally, we will be talking about the green energy aspect of the Smart iLab, which will be discussed briefly. The Smart iLab will be powered by a 55 kilowatt solar energy system, where the inverters are all grid-tied, since power consumption in EEEI is still usually higher than production. There are concerns, however, of overproduction during off hours, in which we have two options. The first option is net metering, but there are permit issues, so we opted for a current limiter system for the SME inverters to automatically limit energy production. The SME inverters we chose also have data monitoring for the solar energy production, which can be accessed through its web UI and can be integrated into Home Assistant as well, as shown in the image here. And by being able to monitor energy consumption and solar energy production, an undergraduate research group was able to research the feasibility of fully powering a classroom with solar energy, as well as performing life cycle cost analysis. The results are shown here, and they found that a 55 kilowatt system can power 4 smart classrooms simultaneously. Through our systems, we are able to enable research in energy monitoring, and hopefully we can enable more research on IoT and smart classrooms in the future. And that concludes my presentation for the Smart iLab project. Thank you, and good afternoon.
Thank you, Sir Adrian. We have time for questions from the audience. Anyone? Ako na naman. Okay, sige, I'll start. So I understand from what I understood is that you're focusing on enhancing the energy efficiency of the laboratory setting. So has this been deployed and used by students, and does it enhance, or is there a way to know if it enhances the collaborative and learning output of the users?
For this teleconferencing setup, we are still in the works for, we already have bought the items to deploy the teleconferencing setup, and we'll be installing the teleconferencing setup around next month after the installation of lighting fixtures next week. And yeah.
Okay.
We'll be checking the efficiency of the teleconferencing setup through other means.
Okay. Thank you, Sir Adrian. Any questions from the audience? Yes, sir.
Good. Thank you for your presentation. In terms of the IoT format for energy efficiency, have you already transitioned to a comprehensive Industry 4.0 enabled facility like a laboratory? Is it in the pipeline, or is it already existing at the moment?
Sorry, what industry? Can you repeat yung industry part?
So Industry 4.0 includes 4 major areas. One is IoT, the other one is the database, data science management, process, and all the others that are actually connected by an algorithm that's actually what you presented for energy efficiency. There is a movement in the industry wherein the facilities are actually Industry 4.0 enabled already. And there is a huge niche that needs to be filled, particularly here in the Philippines, for that particular directions. So I'm just wondering if it is part of the research pipeline to go to that direction?
We are not that familiar with the Industry 4.0.
Sorry.
I know, but if we can research on the Industry 4.0 and we can see if we can integrate that in our research pipeline.
And yeah, because I'm very interested because I'm in the manufacturing area for molecular diagnostics, and part of the competitiveness in the regional scale is an Industry 4.0 enabled facility. I think previously it's called a digital twin, but now it has evolved into that particular aspect. So listening to your presentation, it felt like you are already fulfilling a quarter of that requirement at the regional level. So I'm quite interested and excited if there are initiatives at the local level to actually do that, because there are industries like us interested to transform our facilities into an I4 enabled facility. And that includes this aspect actually.
Yeah, I think we can integrate that pipeline into our research. Thank you, sir. Any more questions?
Any questions? Okay. So let me present to you your certificate of appreciation. This is presented to Sir Adrian Khalil Ais Togonon for sharing their invaluable insight and work on Smart Instructional Laboratory, or Smart iLab, a green, future-ready, and collaborative instructional laboratory for engineering education during the NEECECON 2024, given this 19th day of July 2024 at Novotel Manila Araneta City, Quezon City, Philippines, signed Dr. Lou Andrew Tria. So that concludes our technical session 6. Once again, we extend our heartfelt gratitude to Advanced Energy, Techmark, Keysight Technologies, Embedded Silicon Technology, Solutions Corp, Meralco Analog Devices Incorporated, Presidium.ph Corporation, Road and Schwartz Philippines Incorporated, Alexan Commercial, Maker Lab, Samsung Electronics Philippines Corporation, and Challenge Systems Incorporated for their invaluable support to the NEECECON 2024. Again, this is Meryl Algodon, and thank you for attending this session. Good afternoon.